Hello and welcome back to Calculus 1. Today's section 3.3 Rules of Differentiation. So earlier, in the first section of this chapter, we learned how to take derivatives using the limit definition. So if you wanted to find, let's say you have f of x equals x squared, and you are wondering what the derivative is, you will find the limit as h goes to 0 of x plus h squared minus x squared over h, which would be eventually 2x. So x squared plus 2xh plus h squared minus x squared over h. And then these guys drop, becomes limit, h goes to 0. We factor out h, we get 2x plus h over h. Now these guys cancel, and we get finally limit h goes to 0 of 2x plus h. As h goes to 0, the answer is just 2x. So we have to do this procedure. Now, if I have to do the derivative of x squared plus x, I have to redo the whole procedure. X cubed, redo the whole procedure. Root of x, or anything like that, I have to redo the whole procedure over and over again. So, over time, people figure out the shortcuts. And those shortcuts are the ones which you memorize. It's comparable, I like to compare it, to multiplication table. Because for multiplication, you memorize that 5 times 3 is 15. You sat down and you memorize that. And you use it over and over and over again. And now when I ask you what's 5 times 3, you know it's 15. Now 5 times 3 means 5 plus 5 plus 5, which is 15. By the similar token, you learned what 8 times 9 is. 72, right? Now imagine going 8 plus 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 8. I believe that was 9. So you would get 72. So for convenience, we memorized the shortcut, which was multiplication table, but in the background was addition, repeated addition. Then you memorize that 2 to the 5th power is 32, but that you can figure out by 2 times 2 times 2 times 2 times 2, which is 32. So again, you memorize exponents and so on. So now, instead of calculating that the derivative of x squared is 2x using the procedure, you memorize a formula which allows you to skip this limit procedure. And then you just memorize the formula and quickly compute the derivative. So let's take a look at those formulas that allow us quickly to compute these things. The first one we study with the Leibniz notation now is that the derivative of a constant is 0. So this over here you read as the derivative. There is actually a multiplication symbol that we don't write here, which you get to read as of, and then this is a constant. So how much is the derivative of 10? 0. It's 0, right? Derivative of 10 is 0 because 10 is going to be a horizontal line through 10, and that has no change. So any constant has no change, and because there's no change in constant, derivative is 0. Remember that derivative measures change. So I will write it one more time. The derivative of a constant is 0 because I want to box it. Very simple example. The derivative in respect to x of number 7 is 0. The derivative of pi is 0. So that should be clear. The next one that you are memorizing is the derivative of some kind of exponent. Now, x squared falls into this category, but also root of x and 1 over x to the 10, because exponents could be positive or negative or fractions, right? So all of exponents that you find on x fall into this category. And the answer to that one is n x n minus 1. You will be subtracting 1 on the exponent. Now, this is the one that you would use most of the time, and you'll be very familiar with it. So here it is. The derivative of x squared is just 2x, because the original exponent n was 2. If you compare it to this, right, x squared. So 2 drops in front, and then 2 minus 1 is 1. So we don't write x to the 1, we just write x. Another example of this, x to the 36th power is 36x to the 35. But also, this works as the derivative of square root of x, which, if you use algebra, you rewrite as x to 1/2. And then when you apply the rule, you know that you have to drop the exponent in front and then subtract 1, which gives you 1/2 x to the negative 1/2, which is actually 1 over 2 root x. So the derivative of root x is 1 over 2 root x. Now, are you remembering each individual case? The answer is hell no, you don't. What you are memorizing is the formula up there, and you are using the same formula on each problem. This is why you have to be very careful what you are memorizing and what you are understanding. I am telling you that you are memorizing the red formula, and then you have to understand how to use it within each example. The next problem, if you have 1 over x to the 6, is also in that category. You might say, well, it looks like a division. Well, if you know sufficient algebra, you know that this is x to the minus 6. And all of a sudden, it becomes a problem that we deal with up there. So you will drop negative 6 in front, and then subtract 1 to get negative 7. And the final answer would be negative 6 over x to the 7. So you now see all of the flavors of this one. So no matter what you get as the exponent. Now, we can get fancy, right? Ask for the derivative of 5th root of x cubed. What do you do? X to the 3/5. Very good. So you copy this using basic algebra as x to the 3/5, and then you just go from there. That's going to be 3/5 x to the 3/5 minus 1, which gives you 3/5 x to the negative 2/5. Now, if you want to be fancy, the negative 2 exponent is going down, and the 5th is the 5th root. So you have 3 over 5 5th roots of x squared. So the negative exponent pushes it in denominator, and the denominator in the exponent is making it a root. So there are those algebraic rules that you have to remember in order to master derivatives, such as x to the a over b is b root of x to the a. That's the algebra rule that we use. And also x to negative n is 1 over x to the n. So those are the two rules that I used in these so far. So you see that one rule that we write takes on a lot of different forms, from polynomial to rational function to radical function. So all of them are covered. So we have so far a few of these rules. Let's see more. Again, you are memorizing all of them, because those are shortcuts. If you don't want to memorize these ones, your only other option is to do the long limit procedure every time, which would be equivalent of adding 9/8, right, if you want to skip multiplication. The next rule is the rule that if you are taking the derivative of a constant times some kind of a function, the constant can be kicked out in front of the derivative. Now, immediately to give you an example of this, let's say you are taking the derivative of 3x to the 5. You can see that 3 multiplies x to the 5, and that's the one that can be kicked out in front. So the rule allows us to ignore constant for a while, take the derivative of the basic function because we have formulas for that, and then just multiply that constant back into the answer once we are done. Now, within a week, you will go from here to the final answer right away, because you will just say, oh, 5 times 3 is 15 and minus 1 there is 4. So you'll be doing those automatically. I'm writing all of the steps right now to show where these things come from, but within a week, you guys will go from here directly there in one shot. The next big formula is the formula that says that addition and subtraction of these guys can also be done separately. So if you have two functions added or subtracted, you can take independent derivatives. So this is how we deal with more complicated functions. In this case, I have 3, not 2, but 3 functions. And each one of them will have its own derivative. You can make sure that negative 2 is in front of the second derivative, because by previous rule, we know we can kick constants out. So this would be the derivative of x to the 7 minus 2 times the derivative of x to the 5 plus the derivative of 9. So what's the derivative of x to the 7? And then the next one is, and the last one, plus 0. We don't have to write plus 0 because the derivative of a constant is 0. Now you will in a week go directly there without the intermediate stuff. This is just helping your understanding, but it's no way that you will do the derivatives breaking apart and writing every step out, because you really don't have to. You will just go and say, oh, it's 7x to the 6 minus 10x to the 4, and you're done. The formula is important because it tells you that you are taking derivatives term-wise. X to the 7th has nothing to do with 9 because those are separate terms. It's very important to know now that this doesn't work for multiplication and division. We have special formulas for that. It only works for addition and subtraction. So we have to be a little bit careful about that. So here is now, let's do a few practice problems real quick, and then we'll continue with a few more rules, and then we're done. So what is the derivative of 3x to the 5 minus 4x to the 6 plus 2x? Let's see. All right, so what do we have as the answer? 15x to the fourth, good.
Minus 2 over 3x to the fifth.
Okay.
Plus 3.
Plus 2. Right? 2 times 1 is 2. Now, 2 over 3x to the 5, good? Why not? We have negative 4 times x to the negative 6, right? That's how we rewrite. So,
You have to rewrite it?
yeah, but you can't use the formula if you don't, because you have to have exponent. So that becomes positive 24 x to the negative 7. So it's 24 over x to the 7. And it's positive, right? 24 over x to the 7. There it is. So if you look at it, 2x is 2x to the first power. And when you copy 2 times 1 times x to the 1 minus 1, which is 0. So it's actually 2 times 1, which is 2. You're welcome. All right, cool. So we have that so far. I believe that we only have one more rule for basics. Yep. So just one more. And then we practice a little bit more. So the next rule says that the derivative of e to the x is e to the x. It's the only function in the galaxy that does that. The derivative is itself. So same, you get the same back. There's no example for that. Now, what we actually do is we modify it slightly so that there is something for you to learn. But this is technically the part of what we call the chain rule, which we will study later. So this formula is just temporarily there, and it will be studied later in a better form, better way. So the derivative of this is a e to the ax. And I'm not going to box this in a big rectangle because, as I said, we are going to revisit this formula and learn a better way of dealing with it than just memorizing this. So that's the exponential. Now we are going to upgrade this particular formula 2 times from here. But let's have this basic form. So how much is the derivative of e to the 6x? Very good. It's 6e to the 6x. How much the derivative of 1 over e to the negative x? Let's use basic algebra. Well, we first rewrite it as e to the x, and then the derivative is e to the x. Nice. Good. How much is e to the pi? Yeah. How much is it? Derivative of e to the pi.
Oh, is it pi e?
Pi e or pi minus 1.
It's just equal to pi e.
That's a terrible devil painting of there, or portrait. Or
So this equal pain in the butt.
what is it?
Oh,
Yeah.
that's why I got the devil.
E is the constant, right? Pi is a constant. So think of E as 3, think of pi as 3, so 3 to the 3 is what, 27? Constant. So yeah, they're all constants. The rule works only when there is an x, a variable there, right? No x's in e to the pi. Now, to contrast this, I just want to write that again, derivative of e to the x is e to the x. The derivative of x to the e is e x to the e minus 1. Exponential. And then this is not a polynomial because it has to be integers. So I'll put polynomial. It's called the power rule. Actually, I'll use the power rule. That's the proper mathematical notation, but I'll say polynomial. Polynomial-like in here. You have to distinguish clearly at all times the difference between x squared and 2 to the x. And a lot of mistakes sneak in on those. You only do minus 1 on the exponent when you have a polynomial-like term. So always keep in mind the difference between the two. So this is where your e to the x belongs, and this is where your x to the e belongs. They are different creatures, and different rules apply. Just be careful all the time. So that's it. Now let's take a look at a few exercises. Actually, wait, I think there are also the higher order derivatives before we move on. Higher order derivatives. So what we did so far is the first derivative. But you can chain as many as you want. So you have f of x, then you have f of x prime, then f of x double prime, then f of x triple prime. And then the fourth derivative, the fifth derivative, and so on. You can have as many derivatives as you need. And we are going to use up to the third derivative in this class, up to fourth and fifth derivative in Calc 2, and then go back to first and maybe second derivative in Calc 3. So higher order derivative, and what you do is you just take the derivative. So you take the first derivative, and then you take the first derivative, and the first derivative, and the first derivative. So from any step, no matter where you are, to get to the next step, you will take one more derivative. The notation using Leibniz, we don't have this, it's just again f of x. Over here you will have d dx, d squared over dx squared, d cubed over dx cubed, d fourth over dx to the fourth, and d5 over dx to the 5. These are instructions. So, if I want to find the second derivative for function 6x squared minus 13x plus 2, I will first have to compute the first derivative, which is 12x minus 13, and then I would have to take derivative of that one, which is just 12. So what's the second derivative? Second derivative is 12. Now, if you want to see the same problem done using Leibniz notation, which is the inline writing, rather than starting a new line, you can ask what is the second derivative of 6x squared minus 13x plus 2. Now, second derivative has these squares because that's two of these multiplying each other. So you will first apply one and then you will apply the second. So when I apply the first one, the one closer to the function, I will have to copy the first and I'm applying the second one. I will get the 12x minus 13 and I still have one to apply, which will give me 12. So you have the inline writing using Leibniz notation, and you have the new line writing, which is utilizing something similar to Newton's notation. Leibniz notation is superior, and we'll see why as we move through the course. But you're allowed to use any notation you want. I don't care. There are more notations than these. I told you already that Newton used the dot. So for Newton, function was y, and then the first derivative was y dot, and the second derivative was y with 2 dots. And then 3 with 3 dots. And you really don't need past that for sciences and stuff. Now, Leibniz notation was the derivative and then the second derivative. Right, so that's how Leibniz gave notation. Now, Leibniz notation is superior because it shows that you are taking the derivative in respect to x. And we'll discuss that when the time is right. Why is that so important? And we'll also see problems, word problems, application problems, which is called related rates, that will give us more insight into importance of Leibniz notation. What is the seventh derivative of x squared? Zero. Because the first derivative is 2x, the second derivative is 2, derivative of 2 as a third derivative is 0, and every subsequent derivative after that is going to be 0. So they're all zeros. So the first derivative is 2x, the second derivative is 2, the third derivative is 0, and all other ones up to 7 and beyond 7 are going to remain 0. What is the 104th derivative of e to the x? Yeah. So R, right? This is a good exam question. And then you see someone who didn't pay attention in class. Okay, so the first derivative is e to the x. And then the derivative of that derivative is e to the x. Now the third derivative Now that's problem 1 out of 10 problems, and then the rest of the test is not done, right? Pay attention, right? So the derivative of e to the x is e to the x. Good. Let's take a look at some of the homework exercises, see exactly what textbook thinks you should know. Actually, you know, let me just talk briefly about notation, and then we'll move for derivatives, which is essential for communication, whether it's exam or lab or you at work, it doesn't matter. It's communication. This is standard for the entire world, so let's talk about it. We know that y equals f of x. So the derivative would be as simple as stating y prime is f prime of x, which is okay. But we know that we have more notation for this, which is dy dx, and also d dx of f of x. All of these are notations for the derivative. So I can say the function is, let's say, square root of x. So I can write f prime is 1 over 2 root x. I can write y prime is 1 over 2 root x. I can write the derivative of root x, which is what we had before, is 1 over 2 root x. Or I can say dy dx is equal to 1 over 2 root x. Observe that only one of these contains function and a derivative put together in the same statement. All others, you have pairs. You can pair the problem with any of the answers. This is the only one. The one that is circled is the only one where you see the problem and the solution together. So you have a choice now to write it in line. You are not saying that root x is the same as 1 over 2 root x. It's not. It's different. The derivative of root x is 1 over 2 root x. I hope you see that. Use that language to understand it. The derivative of root x is 1 over 2 root x. Now over here, you're just stating the derivative is 1 over 2 root x. But you have to have this as input. So you either have any of these pairs, right? Like that or like that. Those as pairs. Or you can write just one thing together like this. Now, the way to definitely get the problem wrong is to say that the function is root x and you just write 1 over 2 root x. Now that's clearly garbage, right? Because you are stating over here that the derivative is the same as the function, and it's not. I mean, you have eyes, you see it, it's not, right? It's two different functions. So the only way to get the problem and the derivative linked with the equal sign is to put the operator for differentiation in front of the problem. So you are saying the derivative of this is. The same thing happens, I see this as a symptom a lot. It's curable. Take off a few points on the first test and then it doesn't happen on the second. When people write this, the limit of x squared as x goes to 3 is equal to is is 9. This has nothing to do with anything. That's not the answer. This is not supposed to be there. Over here it says limit of x squared is, the answer is 9. So this Doesn't belong there. So don't write extra limit there. It reminds me of algebra issues. You know, the square root of 9 is equal to square root of 3. It's not. You used up root to change 9 into 3. You don't get to write it again. You just write the answer and you're done. So you used up limit to get 9. You don't write limit again. Over here, you use up operator to change this into that. So you don't write it again. So by that token, you can't write that way. So if you want to write function, then without the operator in front, you have to restart a new line and do this. And you can see that in the way I wrote the entire class today. When I have inline writing with the operator in front, I kept putting the equal sign in front all the time, right? So it was all in line. If I did not use the operators, there was the next line and the next line, and each one of them had the new derivative is equal to, derivative is equal to, and so on. So you will get used to that, but it's extremely important, especially when you have higher order derivatives. All right, now that we cleared notation a little bit, let's see what are the problems that they want you to solve. They want you to, okay, so they tell you that S of t is equal to 4 root t minus 1/4 t to the fourth plus t plus 1. And let's see, what's S prime of t? You don't have to have f of x all the time. You can have anything. 4 root t minus 1/4 t, 4, yep. What do we have? 2 over root t. I like that.
Minus 2 to the third
Perfect.
plus 1.
Nice. So we know that the derivative of root t must be 1 over 2 root t from before, and then 4 and 2 will cancel, right? And then the 4 from the exponent will drop down, and when that one drops down, we have fraction cancel, right? Cool. Now let's see another problem. How about g of x is given as x squared minus 1 over x minus 1? What is the answer? What?
2x. 1.
The answer is 1. So how do we solve this? What do we do first? What do we have to do first? Simplify. So it's x minus 1, x plus 1. These guys cancel. and the derivative of x plus 1. So the whole thing is just x plus 1. Derivative is 1. That's the only way to solve this problem, unless you know the quotient rule. The quotient rule is the one that will deal with the division. All right, let's have one more problem. Oh, very important. Find the equation of the tangent line to y equal e to the x at x equals ln 3. You know the procedure from last class. Where do we start? What's first? Find the derivative, right? So y prime is e to the x. So the slope is e to the ln 3, which is 3. So all it is. We learned last time, except last time we didn't know how to find derivatives quickly and efficiently. We had to use the limit and all of that stuff to get the derivative. And then we plug in the x value and we find the slope. Now we know how to find derivatives quickly, so we can just find the derivative quickly, plug in x, and we immediately have the slope.
Is e to the like when e to the natural log of 5 equal 5 too? Is that how it works?
So now we also have the y value, which would be e to the ln 3, which is also 3. So y equal mx plus b. Y is 3, m is 3, x is ln 3 plus b. So b is 3 minus 3 ln 3. And there you go. Now you could find a lousy decimal for this, but no one cares. This is exact tangent line. At x equals ln 3. So the procedure now for tangent line is much faster and much shorter because we don't have to do the limit procedure to find the derivative, to find the slope. All we need to do now is to find the derivative and plug in x value to get the slope. So when you plug in, as you can see over here, when you plug in x value in the derivative, you get the slope, and when you plug the x value into original function, you get the y value, all of which you need to compute. Because y value, as you can see, is not given to you, right? All they give you is the x value. And then you have to plug that in original. So just use common sense a little bit, right? If you plug in x value in the original equation, you will get the y value for it. And if you plug it in the first derivative, you will get the slope of the tangent line. Now, this problem is going to be studied in every section of chapter 3. Tangent line problem is the most important problem of Calculus 1. So we are going to learn product rule, and the problem will say find the tangent line, but the function will contain product rule, so when you take the derivative, you'll have to use it. You will learn quotient rule, again, tangent line. You will learn chain rule, again, tangent line. Implicit differentiation, again, tangent line. Because tangent line is the central focus of chapter 3. Tangent line is the one that measures the change, the instantaneous change. And that is going to be even more apparent with the mean value theorem and other things that are coming up in this class, in chapter 4 as well. So the tangent line is the one that shows the slope at the point that you are observing. So we use that, actually. We use that a lot if you are following, let's say, how the stock market price of certain stock is changing real time. Let's say your business and you're interested in that stuff. You will see it go erratically, right? Let's do this kind of stuff. But at any point, you know that on this interval here, it's increasing, and then you have a sharp drop, and then it's increasing again, and then decreases a little bit, right? What is the trend? The trend for this span is this much. The trend over here is probably this. The overall trend for the entire thing, that's the average line. And we actually learned that in this class as well. It's just, where do you apply this? Engineering, business, biomedical. There's a lot of application. Calculus drives everything we touch. That's why it's so important, and that's why it's considered elementary mathematics. Because without calculus, you can't perform in any branch, not just science, but in any branch that requires any kind of quantitative, qualitative analysis. So calculus is root of everything. One more problem and then move on. Find the point at which the horizontal tangency occurs for y equals 3x squared minus 12x plus 2. I want to find a point at which the horizontal tangency occurs. The hell is horizontal tangency? Yes.
Just telling you the tangent line is horizontal.
Perfect. Now what does that mean? Nice. Horizontal tangent line means it's flat, means no change, which means its derivative. Sorry, its slope is 0 because it's a horizontal line. Horizontal tangency, horizontal line, slope is 0. You learned that in algebra, that lines that are go this way, slope is positive. Lines that are horizontal, slope is 0. Lines that go this way, slope is negative. And vertical line, slope is infinite. We'll say it does not exist. So horizontal tangent line, horizontal tangency, is the horizontal line whose slope is 0. That means the derivative is 0. Cool. How do you find it now? What do you do? We decoded half of the problem. Now let's see how we actually do it. What else? Yes. Perfect. So in this problem, you know what the slope is, but you don't know which point creates it. It's a backwards problem from the previous one. Previous problem, I gave you x is equal to ln 3. So you did the problem forward. You found the slope. Now I'm giving you slope, 0. And you are supposed to find x at which it happens. So it's a backwards problem. Find the derivative, set it equal to 0, figure out which x gets you there. And that's the answer. So, horizontal tangency implies horizontal line implies slope is equal to 0. And what else is important? And we know that the slope is actually the derivative, so that implies the derivative should be 0. So we quickly find the derivative, which is 6x minus 12. We set that equal to 0 from above, and x is equal to 2. Now, I asked for point. So to find the y value, y of 2 is 3 times 4, so 2 squared minus 12 times 2 plus 2. Y is equal to, that's 12, that's a negative 12, negative 10, right?
Yep.
So point is 2, negative 10. You are going to have a horizontal tangency there. Now that's at the same time the vertex, because horizontal tangency, if you studied what we learned last class, horizontal tangency occurs only when you have min or a max. For a quadratic, you only have min if a is larger than 0, or a max if the a is less than 0. Since we have larger than 0, it's this situation, and that point on the bottom is clearly a minimum. So all of these concepts from stuff you learned before and now the new concepts, they all merge together into this one final picture, which is analysis of functions, that we are going to do in detail in chapter 4. That was just a little sneak preview. So the answer is 2, negative 10. And that ends section 3.3, basic rules of derivatives. It is the stuff that we are memorizing because those are the shortcuts that we do instead of limit procedure. So now when you're looking for tangent line, you no longer have to do the limit. You will simply do the derivative and then plug in the x value that's given to you to find slope, and then continue with the problem in the same way like last time. So that ends this. We'll say bye to the stream and then short break.